Okay, you guys, another one. This is the second last lesson in the probability and counting unit, lesson 3, using combinations. We've come so far, and there is one more big concept left over in 8.4, 8.5. And today we're going to be looking at combinations. So yesterday we looked at permutations, where order is important. Okay, so basically any question that's involving arrangements of letters, digits, or people in positions. When I say positions, I mean like in rows or some sort of specific orientation like that. Those are going to be permutation questions. If you want to find out how many ways that you can choose an object without arranging them, that's a combination question. So let's look at the difference in the next two examples here. So the first question I have here is a permutation question. So take a look at it and you'll notice that it says, okay, so how many ways can you choose a student council of president, vice president, secretary, and treasurer out of 9 candidates? Well, in this question, 2 ways of doing it. You can realize it's a permutation, right? And you can go 9p4, and you can type that in on your calculator. You can use the formula. It's 9 factorial over 4 factorial, and you can work it out, get an answer, okay? Or you can do it this way, where you can say, okay, I need a president, I need a VP, I need a secretary, I need a treasurer. I got 9 options over here, I got 8 options over here, got 7 options over here, and then 6 options over here. You can write it out. In either case, you'll get 3,024. Let's take a look at the combination question. Very similar, but notice the one key difference. So here it says, how many ways can I choose a committee of 4 people out of 9 people? Okay, so in the second question, the order doesn't matter, right? In the first question, I'm choosing the president first and then the vice president. Okay, so if I choose Tom, Sue, Daisy, and Tim in that order, so for those positions, I could choose the same people, but if I chose them in the reverse order, it would be a different arrangement because the positions are different. Okay, in this question, instead of using a permutation, you realize, oh, we just want to know how many ways. Okay, so if I choose Tim, Daisy, Tom, and Sue, in that order, it's no different than choosing them in the opposite order. It's still the same committee of people because there's no assigned positions. Okay, so in this case, instead of going permutation, you're going to use a combination. So you say I got 9, and I'm choosing 4, so that's the symbol for combination. Now you can find this on your calculator. We'll go over the formula in a second, but I just want to show you the difference in the formula. So what is the big difference? Well, the combination accounts for the repetitions. Okay, so see how the formula is almost the same, like you got the 9 factorial on the top, the 4 factorial, but you have this additional 5 factorial. Okay, this accounts for the situations where it is the same committee of people. Okay, so same committee. So that all gets removed, divided out of the question, and there's only 126 ways, right? Versus there's lots of ways to do this, way less to do this. So I just wrote a little note down here, okay? What's next? The actual combination formula. So if the order doesn't matter, then we have a combination. Here's the formula. So it's n factorial on the top, n minus r. So this first part, this is exactly the same as the permutation formula. The only difference is that you have this additional r factorial. Okay? So again, it's on your formula sheet. And I already told you the r factorial in the denominator are the arrangements of identical items which are no longer important in those kinds of questions. So sometimes on the exam, you might have to calculate a couple of these, generally on the no calculator part of the exam if it does come up. So let's just get a little bit of practice doing that. So it's going to be n factorial divided by n minus r. So that's going to be 6 factorial divided by 2 factorial. Now, if you are reducing, just a quick review, expand the biggest factorial until you get to something that you can cancel. So I see a 6 factorial and I got a 6 factorial here. So obviously I stopped expanding it here. But now I can cancel. Whoa. Let's try that again. I can cancel those 2 things. That's equal to 1. 2 factorial is 2, which divides into 8 4 times. So I just have 4 times 7 and I get 28 for this one. This one over here, let's just write out what it would be. So it's n factorial, and then it's n minus r, so you get 2 factorial, and then it's r factorial. So I want to point out that this is the same thing, right? So it's exactly the same, just the order of this down here is different, but it's all multiplication. So this is also going to be 28. And there is something interesting about this, like why are these both equal to the same thing? We're going to investigate that in a moment. Let's take a look at these two examples. So the first one is n factorial, and then n minus r, so you get 4 factorial, and then r factorial, so 3 factorial. So again, expand the 7 factorial until you get to 4 factorial, so 7 times 6 times 5 times 4 factorial. There you have it. So the 4 factorials cancel out to 1. 3 factorial is 6, right? It's 3 times 2 times 1, so that's 6. 6 divided by 6 is 1. So you just have 7 times 5, 35. All right, let's take a look at this one. So you go n factorial. N minus r is 3 factorial, and then r factorial is 4 factorial. So again, you got the same fraction, so it's the same answer. So what is it about these questions that makes the combinations the same? Well, looking at the formula, it sort of makes sense, but the thing that's making them equal each other is that if you add up the r factorials, so two combinations will be the same. If you add up the r factorial, 3 plus 4, and you get 7. So if you get the n value, then those two combinations will be identical. And that is an important property to note because sometimes they use that on the exam. So the important conclusion is if we go and figure out what this equals, and I would say let's just be lazy on this one and we'll just go type it in on our calculator. If you type this one in on your calculator, you get 1. So there was an exam question. It was like a theory question one time, and it basically was like, hey, if this combination equals 1, then what does this one equal? Okay, and the thing to realize is, hey, when I add up the r values, I get the n value of 14. When that's the case, they equal the same. So this one would also equal 1. I don't need to type it in on my calculator because I know about that property. Okay, so if r values add up to the n value, then those combinations, so I'm just going to put those combs, are the same value. So that would be sort of the conclusion to write down. Okay, basically let's do a bunch of questions. Your best defense in the probability unit is to do as many questions as you can, because after a while they start hopefully, looking the same. So this one, my favorite question is the Lotto Max question. How likely are you to win the Lotto Max? Well, let's take a look. Basically, if you shouldn't have played the Lotto Max unless you're at least 18. But so basically a player chooses 7 numbers from 1 to 49. To win the jackpot, you got to match all 7 numbers that are randomly drawn every week. Okay, so basically the question is, how many combinations of the 7 numbers are possible? So if I choose my 7 numbers, and say I just choose 1, 2, 3, 4, 5, 6, 7, those are my 7 numbers, the order the numbers get drawn in don't matter. Okay, so if they draw a 45, a 47, and a 40, and a 50, it doesn't matter that they were drawn in that order. All you got to do is match all the numbers to win. Okay, so this is a combination question because the order doesn't matter. Okay, I don't need to match the numbers in order. I just need to match the numbers. So there's 49 possible numbers, and you are going to choose 7 of them. Now, this is definitely something you type in to your calculator, and you're going to get 85,900,584. Okay, so if you buy 1 ticket, you got a 1 in that chance of winning. So it's about a 1 in 86 million chance. That's why, week to week, sometimes you see it not being 1 because, theoretically you got to sell about 86 million tickets before someone wins. But then you get weeks where like 5 people win, right? So you never know, but your odds of winning are very, very low. Okay. This one, a fundraising committee is to be chosen from a group of 8 students. How many ways can a committee of 5 students be chosen? Okay. So you need to think in this question. Is it a permutation or is it a combination? So if there's no specific positions for the 5 students, then it doesn't matter what order you choose them in, right? Everybody's on the committee, okay? So one of those equal opportunity committees, okay? No vice president, stuff like that. So this is a combination question. So you got 8 people, and you're going to choose 5 of them. So 8C5, type it in on your calculator, and you get 56 ways. Okay, part B. What if it's just 3 students being chosen? Well, it's going to be 8C3. And hey, check it out. 5 plus 3 is 8. So these two combinations have the same value. It's going to be 56 again. Save yourself a little bit of time. Okay, we can go ahead and take a look at the next question. Got a bunch, actually. In how many ways can 6 teams in a league play each other team only once? Okay, so they can only play each other once. The order they play in doesn't matter, right? So you got teams A, B, C, D, E, F. Doesn't matter if A plays F first or if A plays B first. You know, they've played, or if B plays A, right? Or if F plays A, that's the same thing as A playing F. Okay, so this is not a permutation, it's a combination. That's the hardest part of most probability questions, is deciding which one is it. Okay, so if it's a combination, you're almost invariably always going to use the formula. It's just easier to use the formula. Okay, so 6 choose 2, because you got 6 teams, and they just need to, 2 teams play each other at once, right? So you're picking 2 teams at a time, is one way to think of it. When you type that in on your calculator, there's only 15 ways for that to happen. Number 4, there are 10 boys and 8 girls in a class. How many ways can a committee of 10 be chosen? So there's no restrictions on, how many girls, how many boys. So essentially, your n value is 10 plus 8 or 18. And because there's no positions on the committee, you simply just get chosen. It's 18 choose 10. Take a moment to type it in on your calculator. You're not generally expected to calculate these out by hand unless the numbers are smaller. Okay, so there's that many ways, about 43,000 ways. Let's see. This one's interesting. So 10 boys and 8 girls try out for a co-ed volleyball team. If each player has an equal chance, how many ways can a team of 4 boys and 4 girls be chosen? So this one does have a restriction. Now, it doesn't matter as far as the composition of the team goes if I choose my 4 boys first and then my 4 girls. Or my 4 girls and then my 4 boys. It's going to be the same team. Right? It doesn't matter what order we pick them in. So what I recommend you do is be like, okay, I'm going to choose my boys, and then I'm going to choose my girls. Okay? So for the boys, you got to look at specifically just the boys. There's 10, and we're choosing 4 of them. Okay? Times, there's 8 girls, and we're choosing 4 of them. So calculate these separately, multiply them together, and you'll get 14,700 different teams. Wow. So when you don't get chosen for that team, wow, you had a lot of chances. Oh, you guys. Okay, final example kind of brings everything together. So let's see. How many ways can you choose a committee of 5 from 6 boys and 7 girls if you want a majority to be girls? So this is going to have some cases. Okay, so it's bringing everything together in the sense that we have a question that has cases, so we'll be adding them together, and you need to figure out, is it a combination or a permutation? It's definitely a combination because the committee doesn't have any specific positions, right? So how can you have a majority of girls? Well, there's 5. There's 5 people on the committee. Okay, so to have a majority of girls, you could simply just say, well, I could have 5 girls and 0 boys, right? Or, so we're going to add to it, what if you had 4 girls and 1 boy? That's still a majority of girls. Or you could have 3 girls and 2 boys. Now, if you go to 2 girls, 3 boys, you no longer have a majority of girls, so those are going to be your 3 cases. So start with the easy one, 5 girls. Well, there's 7 girls to choose from, and I need to pick 5 times I have 6 boys and I'm going to choose 0. So this actually, if you type it in, is going to be 1. I just wanted to point out that 6C0 is 1. 7 choose 5. When you plug it in, you're going to get 21. So maybe circle that, whatever. That's sort of your first case. So we're going to add that to the next one, where out of the 7 girls, we're choosing 4 of them, times 6 boys, we're choosing 1. So give you a second to type that in on your calculator. I do believe this is going to be 6, right? There's only 6 ways to choose one boy once, but you can double check on your calculator. When you multiply them together, either way, you're going to get 210. You can circle that. We're almost done. We're going to pick 3 girls and 2 boys. So 7, choose 3 girls, times 6, choose 2 boys. Type that in on your calculator. And this one's going to be a bit bigger, 525. So add them all up. That's the addition principle of the fundamental counting principle. And you're going to get 756 ways. So that's a question that sort of applies a lot of the concepts that we've learned so far in this unit. And just to wrap it up, I got 2 questions here. It's more review than anything, but these are basically different question types that we saw coming up to this point. And definitely, like, my caution is, stick with it. Like, the hardest part of this unit is sort of distinguishing between all the different question types, and then, of course, knowing your probability rules and facts. So how many ways can 3 identical, now keyword is identical, so we got some repetitions here. So repetitions we divide out using factorial. You'll recall from a couple lessons ago. So we got 3 identical French texts, 4 identical math texts, and 3 identical geography texts to be arranged on a shelf. Okay. It doesn't matter. It doesn't have any stipulations about, we did a question where they had to be kept together by group. It's just how many ways can you arrange these textbooks on a shelf? So in total, how many textbooks do we have? We got 3 plus 4 plus 3, so we got 10 textbooks. Okay, so there's 10 factorial ways to arrange 10 textbooks in a row. But because some of them are repetitious or identical, we need to divide by the number of repetitions factorial. We learned that back, I think it was in 8.1. So you might want to go review that if that's not making sense to you. So for the French text, we need to divide by 3 factorial to get rid of all the repetitions. For the math text, we need to divide by 4 factorial, and for the geography text, there's 3 identical ones, so we divide by 3 factorial. Now, this would probably be a calculator question because the numbers are getting pretty big. So, type it in on your calculator. Make sure you're using brackets for the denominator. I actually didn't calculate it out, and I don't even think I have a calculator handy. I wish I could give you an answer. I found a calculator. Does it have a factorial button? Oh, it does have a factorial button. So the 10 factorial, might as well write it out, is this. Looks like 3,628,800. Oh, yeah. Very nice number. 3 factorial is 6. 4 factorial is 24. Remember, I recommend that you memorize those ones. So there you go. Give you a little bit of work, intermediate work. So I'm going to divide by basically 6 times 6 times 24. And there we go. You get 4,200. Wow, so many ways. All right. Last question. How many ways can 3 different French texts, 4 different math texts, and 3 different geography texts be arranged on a shelf if they must stay together by subject? So that's the famous question that we were doing the other day. So draw your spaces. Okay, and I guess when I'm looking at this question, I'm like, I'm not using a combination, but I'm using this method here, which is basically some sort of permutation, right? So if we just arbitrarily say, like, okay, the order they come in the question, we got our French books, we got our math books, and we got our geography books. So within the French group, there's 3 different texts. So there's 3 factorial ways to arrange them within that group. Within the math group, there's 4 texts. So there's 4 factorial ways to arrange those math texts. 3 different geo texts. So 3 factorial ways to arrange those. Now remember, you're multiplying. Don't forget that this is not the only way I can arrange the groups, right? So I just arbitrarily chose to go French, math, geology, but I could put the geology out in front. That'd be a different arrangement. So it'd be a different way of doing this question. So how many groups are there? There's 1, 2, 3. So there's 3 factorial ways or 6 ways to arrange these different subjects together into different groups. So overall, that's your work. Now, I need to type it in on my calculator, but if you're looking for the intermediate work, it's going to be 6 times 24 times 6 times 6. 6, of course. To basically have, here we go, there are 5,184 ways to do this. Wow, all the possibilities to arrange them textbooks. So I do have a final thought today before you go and try exercise 8.3. And I posted on Teams the supplementary sheets, and they're also in the descriptions of the videos. Final thought, and this is actually a question that was on an exam somewhat recently. It was a theory question, and it was just like basically, why should it not be called a combination lock? Okay, so if you got say you got like one of those locks that gets 3 numbers and the code is 1, 2, 3. Should it be called a combination lock? Okay, so for combinations, order doesn't matter. Okay, so if it was a true combination lock, as long as I got the 3 digits correct in any order, it should open the lock. But really, it should be called a permutation lock. Why? Because the order matters. Okay, so not only do I need to get the correct 3 digits, I need to have them in the correct order. So if I enter the code 321, it's not going to open. If I enter 213, it's not going to open. It needs to be the correct code 123. So when the order matters, these are all different arrangements. That's a permutation. So that was a theory question, 2-mark theory question once on the exam. So anyways, we are done. We got one sort of large lesson coming up. It is the last one. And there's a lot of things that come out of it. It is Pascal's triangle, very important. We love triangles and we love Pascal. So I will see you guys next time, and I just wish you a good one. Bye-bye. Bye-bye.